Sorry we got cut off on that last session, but I'm back on track now. I just had gone through how I got this answer longhand. One other way I want to point out you could think about this. M to the second divided by M to the fifth. Where are there more M's, on the top or on the bottom? The bottom. And how many more? 3 more. So the M's on the top cancel, put your placeholder, and then you have 3 M's remaining. So that's another way you can think about a problem like this. Going up, we have 2 more examples. Problem D. Divide anything, we need to simplify that denominator because we have a product raised to a power. None can be simplified in the numerator, so that's the same. But the denominator, for lack of a better word, we can distribute that exponent of 2, so it's d squared times e squared. And now we can divide. The common base is d, subtract those exponents, minus 2 is 2, and e minus 2 is 1. I'm not going to write the 1. You could if you wanted. An understood 1 is in the exponent if there's not one. This last example, if you wanted to do this motion, go right ahead, but that takes so much longer. I break this apart into the common bases, the 3 and the 3 squared. Where are there more 3's? There's more in the bottom. There's 1 more. So this 3 cancels, and you have 1 3 left in the bottom. With the first, also you can cancel. There's 4 3's multiplied together on the top and on the bottom. You can cancel out 3 of them. You can cancel out 3 of these. And then you're just left with 1 4 in the bottom because there's more 4's down there. With your 5's, there's more 5's in the numerator. So 3 of the 5's cancel, and you're left with 2 in the numerator. 5 times 5 is 25. 3 times 4 is 12. And there you have your answer. We'll move on to talk about the next rule. How to deal with powers of quotients or powers of fractions. Still means the same thing, repeated multiplication, 2/3 times 2/3 times 2/3, which is 2 times 2 times 2, 2 to the third, over 3 to the third. 2 to the third is 8, 2 to the third is 27. When you have a fraction raised to a power, the exponent goes to both the numerator and the denominator. There's no need to write out this longhand. I was just doing it to show you. You can just go with the 2 to the third and 3 to the third. Write down the answer. So 1 to the fifth, or 1/5 to the fifth. That would be 1 to the fifth over 5 to the fifth. 1 times 1 times 1 times 1 times 1 is 1. 5 to the fifth, I believe that's 3,125. But check that. If I'm wrong, let me know in class tomorrow. I trust that you guys will correct if I need it. Example B. This is a more complicated quotient, and the whole thing is raised to the 4th power. So everything in the numerator raised to the 4th, everything in the denominator raised to the 4th. That would be 3 to the 4th, and d to the 2nd to the 4th. Here you have a power raised to a power. Remember what you do? Hopefully you remember you multiply those. 2 times 4 is 8. In the denominator, e raised to the 4th, and f raised to the 4th. Is there anything else to do? Don't have any negative exponents, don't have any common bases that can be divided. The only thing I see to do, you can simplify 3 to the 4th. That's 81. 81 d to the 8th over e to the 4th, f to the 4th. Finally, another complex quotient raised to a power. If you're the order of operations, what's the very first step you do in the order of operations? If you said simplify everything in parentheses, you are correct. Let's do that here. Simplify what's in the parentheses. We have common bases of a's divided by each other, common base of b's divided by each other. So let's do that division. A to the third divided by a to the second. If you subtract those exponents, you get a to the first. I'm not going to write 1, it's understood. B to the third divided by b to the first. Understood, 1. That's what you get when you simplify inside the parentheses. Raised power. We have a power of a product. So every one of those factors in the parentheses is raised to the 3rd power. So the answer is a to the 3rd, b to the 3rd. This is how you deal with a quotient that has a power. One thing I want to point out, this is what you do if the exponent is positive. Next, we're going to look at what you do when it is negative. If the exponent is negative, The rule is a quotient that's raised to a negative equals the reciprocal of the quotient raised to the positive power. So we have a quotient with a negative power. It's going to be equal to the reciprocal of the quotient. So the reciprocal of 2/3 is 3/2 raised to the positive power. So when you reciprocate the base, then you can change the exponent to positive. And that would be 3 to the 4th over 2 to the 4th, which is 81 over 16. Let's work these examples. If you want to do them first, hit pause, do it on your own, then turn this video back on. 1/4, -2 power. -2 power means you're going to reciprocate that fraction. The reciprocal of 1/4 is just plain old 4. 4 over 1. Make that power positive now. 4 squared is 16. Another quotient, 2 to the power. Do the reciprocal of the quotient, making the denominator become the numerator, then become the denominator. All of this would be raised to the positive 1 power. That doesn't change anything. I'm not going to write it. It's just extra. You can if you want, but I'm not going to. Finally, another negative exponent. We have a quotient as the base. So flip that quotient. Make the 2x the numerator, the y cubed the denominator. I'm going to put that in parentheses because that whole thing is then raised to the second power. So now everything in here raised to the second. 2 to the second is 4. X to the second, x to the second. Y to the third raised to the second is y to the 6th. We can multiply those exponents. That's negative power of quotients. Next thing we're going to look at is how to calculate scientific notation. I have two problems here. All scientific notation, we have a division problem. You could, if you wanted to, write this out in standard form and divide them, but I think that you're going to be working with really long numbers and it's so much easier. When you're working with these problems, I like to write them as a fraction. You don't have to. That's just how I like to do it. Oops. And then essentially, you're just going to kind of break this into parts and deal with the 3 and 6. What is 3 divided by 6? It's 1/2 or 0.5. And then you divide your powers of 10. 10 to the 10th divided by 10 to the 6th. Have the same base. Subtract the exponent. So you have 10 to the 4th. And that would be your answer. Now we don't have any specific directions here. If the directions said put your answer in scientific notation, we'd have to evaluate this answer. Is this answer in scientific notation? And actually, it's not. Do you know why it's not? It's all about that number. Remember what that number is supposed to be between? It's supposed to be between 1 and 10, and it's not. So how can I miss decimal points to have a number between 1 and 10? If I move it to the right one place, that would give me a 5. But if you move decimal place here, then you have to change that exponent. I've moved it over one place already. So now I am only going to need to move it or one places, so it's 10 to the 3rd. This would be the final answer in scientific notation. It's equivalent to this answer in blue, but this is in scientific notation. This is not. If we had to write it in standard notation, hopefully remember that it would just be 5,000. Take the decimal, move it 3 places to the right because it's positive power. Alright, I want y'all to do the second problem on your own. Hit pause, solve it just like I solved this first one. See if you get the same that I'm going to get. .3 divided by 3 is 1.1. 10 to the 6th divided by 10 to the 8th is 10 to the -2. Here's the answer. Is that answer in notation? It is. Don't have to change anything. Just for practice, let's change it to standard notation. Negative exponent means move the decimal 2 places to the left or backwards. So I move 1, and then to move one more place, I'm going to have to put a decimal. Or a 0, sorry. So the answer in red is in standard notation. In blue, it's scientific notation. Alright, finally we have an application. These types of problems are really, what's going on in our current economy is perfect for these types of problems. We can talk about the deficit that the United States budget is in. And we could write that in scientific notation because it's such a big number. This example is about a school system. The Colorado Department of Education spent about 4.408 times 10 to the 9th dollars in the fiscal year 2004 to 2005 in their public schools. There were about 7.6 times 10 to the 5th students enrolled in the public schools. What was the average spending per student? And they want us to write the answer in standard form. Our numbers are in scientific notation, but they want the answer standard. You could change this to standard and this to standard and calculate, but it's much easier to calculate in scientific notation and change it at the end. So to find the average spending per student, you take the amount of money total that they had, 4.408 times 10 to the 9th. That's the total amount of money that the whole system had, and divide it by how many students there were, and that will give you the price per student. So we need to divide 4.408 divided by 7.6. I'm going to grab my calculator. Actually, I've already done the division, and I got the answer to be 0.58. 0.58 times, now divide your powers of 10. That's going to be 10 fourths. Answer, except that didn't write it in standard form. So that decimal place 4 places to the positive, so 5, 8. And this is how much money the Colorado Department of Education spent per student in 2004, $5,800. Alright, that's the information on what I want you to do right now. Get out a piece of paper, get out a pencil, put those calculators, and I want you to answer these 7 problems on a piece of paper. I'm not going to go over the answers with you right now. Hit pause, answer the questions, bring them with you to class, and then we'll check them in class.